So coming back to where we started with graphene, and graphene is known for nanoelectronics because of high achievable mobility, because of its linear dispersion, and gate tunability and ballistic transport. From the point of spintronics, these carbon atoms have very low spin-orbit coupling and no hyperfine spin interaction, which means that it's theoretically very long spin diffusion length is possible with a very high spin lifetime. And this has propelled research interest in exploring graphene for spintronics. For example, this is the first seminal work by Tombras et al. In 2007, where they have used an exfoliated sheet of graphene, and these are cobalt electrodes, and they tried to transport spin currents by injecting electric currents from this cobalt electrode into graphene and detecting with another electrode, similar electrode placed at beyond 2 micrometers distance. And if we compare this device with the same group's device on a metal spin valve, one could clearly see that a lot of improvement is made, and this spin transport achieved in this device is achieved at room temperature. So the way it is done is basically that one can inject electrically, and one can change the chemical potential of electrons, spin polarized electrons, detect that by flipping this magnets from parallel to anti-parallel configuration, and that leads to obtaining this spin Wald signal. This is a spin transport. In case of spin transition, a perpendicular magnetic field is applied, whereby the electrons presses about the magnetic field, and there is a continuous change in the spin signal, which can be fitted to an equation that contains a diffusion part, a relaxation part, and a precession part. And from there, the spin lifetime can be determined. So a lot of attempts have been done, and state-of-the-art reports say today that the spin diffusion length of 10 micrometers and the spin lifetime of 1 nanosecond can be achieved in graphene spintronics. So what started from graphene spintronic, now we have 2D spintronics. This is the review. This is another review. These are some recent reviews. And I tried to put here an oversimplified summary of what has happened, like understanding the spin relaxation physics, enhancements in spin transport, use of barriers like hexagonal boron nitride, proximity effects, spin charge interconversion, thermoelectric devices, and spin valley devices. So a lot of things have happened. Despite all these effects, if we really want to harness all these effects, at the base, the platform is graphene. So we need to realize high efficient quality spin transport in graphene, and not only in graphene, but it's in any form of graphene, but a large scale form of graphene, which means the challenge boils down to a large scale implementation of this is the necessity, and also the reliability of such a thing. And this has actually been the motivation for my research for the last several years. So to go from here to here, there are some challenges, because here one can obtain single crystals. Here the intrinsic nature is very polycrystalline with grain boundaries, defects, and corrugations, and one can keep on adding more and more fabrication related defects. Despite that spin transport has been demonstrated, it is feasible to see spin transport in this kind of devices made of carbon chemical vapor deposited graphene. So the question is that those values are of the order of 150 picoseconds. Can we go to higher values? Can we enhance spin communication through vapor scale graphene? This is the question that I've been exploring since several years, and we have been able to see that with channel length the resistance increases, scales linearly with a reasonable mobility of even commercially available chemical vapor deposited graphene. And what we have been able to see is that in this report, which we published in 2015 with some of my ex-colleagues, we have been able to see that spin transport is possible in commercial graphene over 16 micrometers at room temperature. And this yields a spin diffusion length of 6 micrometers, which is higher and competitive value compared with when we compare with the state-of-the-art reports in sophisticated devices that have been prepared on high mobility graphene. Also, we obtain a spin lifetime of 1 nanosecond. So this is the spin bring contacts closer and closer, which means that there is an influence of contacts, which actually shifts this Dirac point here. As a consequence of that, what we see is that the sheet resistance of graphene changes also, and the contact resistance of these contacts with graphene also, the interface resistance also changes. So when we took this into account, we started to realize that we can keep electrodes very far from one another, and we started investigating extremely long channels that are much bigger than the kind of exfoliated graphene sheets that one can get. So for the first time, you can see that this is 10 micrometers, this is 13 micrometer channel, this is 51 micrometer channel, and this is 36 micrometer channel, which is the longest channel in which spin signal was reliably, robustly observed. And we could go even up to 45 micrometers spin transport. We can clearly detect spin transport in these channels. And we could also do the spin precision experiments, and we obtained a maximum spin diffusion length of 13.6 micrometers at room temperature. So it's like a spin diffusion length of 14 micrometers nearly, and a spin lifetime of 3.5 nanoseconds, which is the highest. And we could even see that these measurements, when we performed a measurement, even after 10 months, we saw spin transport. And all these things showed a specific kind of behavior that indicated that if we also saw that even under ambient conditions, when we opened the valve and allowed the ambient conditions, we could still see spin transport and obtain the same kind of values of spin diffusion length and spin lifetime. So spin transport is quite robust in this case. So, and when we tried to see the dependence of momentum relaxation with the spin relaxation times due to Elliott-Jaffet or Dekanov Pearl, what we see that in this kind of case, we see that the spin relaxation due to Dekanov Pearl mechanism seems to be the most dominant mechanism. So we ignored the spin relaxation due to Elliott-Jaffet. So instead of the conventional method, we tried to employ only the Dekanov Pearl mechanism to evaluate the spin diffusion length. So what we tried to do is to make an empirical model to take a spin orbit coupling below the contact and in the bulk of graphene, different kinds of values for spin orbit coupling, and try to find an effective value using this empirical value. And we tried to, for different lengths of separation, we tried to calculate the spin orbit coupling from the experimental values of lambda. So we got these values and we tried to plot them and fit with this model, and we find that that beyond a certain point, the spin orbit coupling becomes like 20 milli-electron volts, which is what one can expect for graphene on large-scale graphene on a standard silicon substrates. And we see that when we try to see what is the value, the floor that one can get here, spin orbit coupling, and put it back here, that value like 18.5 microelectron volts, we obtain that we could go up to a maximum of 15 micrometers, which means that we hit the roof of what is available as the maximum spin diffusion length that's available for chemical vapor deposited graphene. So I have many slides, but I can stop at any stage having said one story about how contacts influence spin diffusion length in graphene. What we try to further investigate is that these contacts are much more complex. So to do that, we try to see how metal oxides, which we use between the cobalt and the graphene sheet, influence beyond charge transfer. So in order to do that, we try to deposit graphene on the metal oxide on top of graphene sheet. And we tried to measure its electrical properties and did some complementary experiments to understand what happens to the metal oxide graphene interface, which is key for efficient spin injection. So this is work which we recently published. What we observed is that the metal oxide shifts the Dirac point quite a lot. For both, we used two kinds of oxides which are widely used in graphene spintronics: aluminum oxide and titanium dioxide. With titanium dioxide, usually high spin lifetimes beyond nanoseconds are detected. With aluminum oxide, there has always been a problem with pinholes, and spin lifetimes of 100 or 200 picoseconds has been reported, maximum values broadly. So for both these kind of oxides, we saw that there is p-type doping for both these kind of oxides. And there is a huge change in the Dirac point, shift in the Dirac point. So a lot of doping happens due to charge transfer. And it can be seen that the mobilities for many devices, for both kind of aluminum oxide and titanium dioxide interfaces, we saw that the mobility remains more or less the same before and after. So, and also the minimum conductivity that one can get these points. So what it means is that the electrical properties of the sheets are more or less intact, which means but despite these things, what we observed is that we tried to do some complementary experiments like a photoelectron spectroscopy to determine if these oxides are fully oxidized. And what we see from the energies where we can expect this to happen, we saw that the titanium and aluminum are nearly fully oxidized. At the same time, we could also pick up some contributions in case of titanium and aluminum oxide of sp3 contributions that are dominant compared to what pristine graphene case. And when we tried to do the Raman spectroscopy of all these samples, interestingly, for the aluminum oxide case, we see the emergence of a sp3 defect D band, which is absent for pristine graphene and graphene with titanium dioxide. So there must be something happening, extra additional titanium sp3 defects. So the story turns out to be somewhat like this, that these sp3 defects, so in order to understand how the bonding takes place, we did DFT calculations, density functional theory calculations, which reveal that in case of aluminum oxide, based on how it interfaces with graphene, there can be additional p-type doping and sp3 defects, which can offer a magnetic moment of up to 1 Bohr magneton, which can actually influence spin relaxation, enhance spin relaxation through the resonant scattering mechanism. So this is a new insight which could also contribute to the explanation of why, in addition to pinholes, the spin relaxation in graphene is found to be quenched in case of aluminum oxide based barriers, and why titanium dioxide shows superior spin lifetimes. Because these contacts are quite resistive in case of graphene spin devices, it's also important to know how much electrical spin injection we can do, up to what currents we can use these devices for high performance graphene spintronic devices. So in order to understand that, what we try to do is to compare with what is state of the art in graphene is 10 to the power of 8 ampere per centimeter square, which is quite higher than what is 1 or 2 orders higher than even copper, the current density. But then even for state of the art polycrystalline graphene, it's higher, but then it's nearly 1 order less than what is reported in small single crystalline graphene sheets. So we tried to investigate this problem because this has practical relevance, and we used again large-scale chemical vapor deposit graphene. And this work has been recently just accepted. It is online. You can search high current limits in chemical vapor deposited graphene spintronic devices. It's published in Nano Research. So what we see is that the problem comes from here. If you see, this is an atomic force microscopy picture of commercial graphene, and you can see these ripples. In addition, there are grain boundaries, and the grain sizes are anywhere range between a few hundred nanometers to several microns, like less than 5 microns. And then this is an AFM picture of a device. So you can see that within a scale of 3 micrometers, we can see a lot of mess here. So that mess means ripples and grain boundaries, which acts as hotspots at these grain boundaries. In this report, where they have seen that the performance is compromised because of these things. So this is a problem of practical relevance. In addition, you can also see that there are thermoelectric effects where heating and cooling takes place in different places. So polycrystallinity and contact resistance and thermoelectric effects, these are some challenges. So we tried to investigate in different devices, and what we found is that you can see that this is an IV characteristic curve for a device here. So one can see what is the tunnel barrier nonlinearity that can be obtained here. And after a certain current voltage, you can see that it can withstand up to 6 milliamperes. Then the graphene sheet breaks. It's a two-terminal measurement. It means that it includes the contact resistances of these two contacts as well as the sheet resistance. In order to see what happens to graphene clearly, we tried to investigate, and we saw for the first time that there are two regimes. One regime up to which is a reversible regime where graphene stays okay, and then there is a regime where it starts to degrade for each cycle. So we perform different cycles before reaching the breaking point. And we could see clearly that we could go to 10 to the power of 8 ampere per centimeter square without any degradation for certain samples. So these are different samples with different sheet resistances. So the key is to have low sheet resistance, and that can give a maximum of up to 5.5 instead of 8 ampere per centimeter square. It's possible to go, in principle, it's possible to go to lower values. So very high current density can be realized in CVD graphene, despite the resistance, high resistance of the tunnel barriers, which is needed to avoid the circumvent the conductivity mismatch problem for efficient spin injection. And despite this high current, so we try to also explore if spin transport at all is feasible at these high currents. What you can see here is that it is possible up to 1 milliampere, which is like 10 to the power of 8 ampere per centimeter square. And this is the highest reported value. But then the spin signal actually gets quenched, and this happens due to some magnon excitations at high voltage and heating effects at the interfaces. So we need to improve on this. We need to find out some other kind of barriers where this doesn't happen, efficient barriers. So then what we try to investigate. How much time I have? Do I have how much time? Okay, great. So the interfaces clearly impact graphene, as well as to what currents we can make high performance devices out of chemical vapor deposit graphene is now clear to us. So again, our approach is to see what happens to large scale graphene on different kind of substrates, especially substrates influence graphene. And since graphene and other 2D materials are very resilient, it's important to see if we can take graphene towards flexible graphene spintronic devices. But there can be challenges, because the conventional flexible substrates like polyamide, polyethylene terephthalate, or polyethylene naphthalate, PN substrate, they often come with a lot of roughness, surface roughness. So in order to establish some kind of stable contacts, we have to make even lithography on this, and we have to lay some electrodes. And how the magnetic texture of those electrodes due to the roughness is influenced is unclear. And also there are fabrication challenges, and nature of transport on this kind of substrate is not clear. Especially in the field, what we are aware of is that if we want a high mobility, we need to encapsulate graphene or put it on top of hexagonal boron nitride, which is atomically flat. So it is possible to suspend or to put on top of atomically flat substrate to avoid substrate-induced scattering potentials and obtain very high mobilities. But on this kind of substrate, we do not know, because this has more roughness than the conventional silicon dioxide substrate data that I spoke. But then this is quite compelling, because if we see compared to normal materials, like for instance silicon, which can withstand a strain of 1.5%, it can almost, the 2D materials can actually go up to 10% of strain levels, which makes them ideal for flexible nanoelectronics. In order to integrate any kind of these devices, spintronic applications of 2D materials into this, it's important that we try to investigate these, which is what we tried to do. So we made some devices on flexible substrates with electrodes, but to see spin transport, if it is at all possible in case of graphene on this curved substrate. So first, to establish the resilience of these contacts, we performed magneto-optic Kerr effect on these wires, on millions of these wires, and we could see that clearly for nanowires they have very much resilience compared to thin films, which break after a stress of 3 gigapascal on the same kind of substrates. So once we established it, we also tried to investigate this. And in addition, the magnetic properties do not change much because of the ultra-low magnetostriction, which means the coercivity doesn't change much when you bend a wire, which makes it very resilient. So we tried to investigate that, and we could clearly see that that these devices show spin transport up to 15 micrometers, and we can also even measure them by cooling the wires that connect them to low temperatures. So spin transport on this kind of substrate is very robust. At the same time, it's also very high diffusive, which could happen only when the electrons are high, or the carriers have high electron mobility. So this is, you can see that at different temperatures we could do it. We could observe clearly the spin transport in these different devices. But then we could also observe a spin precision that yields a diffusion constant which is unusually high compared to our devices that we make on normal silicon dioxide substrate. So the value in this case is something like 10 to 20 times enhanced compared to graphene on the similar kind of devices that we make. And quite there is an enhancement also in the spin signal, and this can only happen if the mobility is high. So we found that the mobility was one order higher in this kind of substrate compared to silicon dioxide, which we established through Hall measurements. So to conclude, it's important to understand how contacts and substrate can influence in order to push graphene to practical circuits, to explore more advanced circuits. And to do that, we have been able to see that it's possible to achieve maximum spin currents by contact engineering, by minimizing the contact effect on graphene doping. We can do that, and we also see that the contacts are not very simple. They can be quite complex. They can involve magnetic moments, which in addition to pinholes, even though for titanium dioxide and aluminum oxide, if we do atomic force microscopy, they both reveal the same kind of topography, which means that in one case it is pinholes, they both can have pinholes. So it seems that magnetic moments influence, and then we also see that it's possible to push very high currents through graphene for high performance graphene spintronics, and we can also make such devices on flexible substrates, which opens gateways for other 2D spintronic devices. And these bring many new exciting opportunities which we are exploring. We have some of these results in this review which we elaborated, so you can get this information from there. I thank you once again, the organizers, and thank you all for this your kind attention. And I also would like to acknowledge the agencies that enable this research. Thank you very much.
Thank you, Venkata, for the nice talk. On the last part, on the strain, so do you have some measurements of the spin diffusion in the function of a strain? Why are you
This is a
performing
very
experiments?
challenging experiment, and for this we are trying to build a cryostat. Now we have reached a stage that we had to redesign everything to see that how in situ strain can influence spin transport. And so now we will be starting these experiments in a month's time. But initial experiments that we did, we got the same question from the referee. So what we tried to do is to bend it manually and put it and measure it, and we could still see spin transport. That did not, I mean, it was not so conclusive to make a statement about that this does this. But strain can do many things. It can increase mobility, it can change the effective mass of electron, and many interesting things can happen. So we are looking forward to these exciting new experiments.
Thank you.
Thank you.
Maybe you can ask in the later. We need more. Sorry. Thanks a lot, Venkata, for coming.
Thank you.